Controlling AC power with Arduino. I'm your host, Lewis Laughlin. We are going to be looking at how to use the Arduino microcontroller to control 120 or 240 volt AC power. In this video, we're going to be discussing both electronics and programming, and then we will view a live video of the circuitry actually working. So let's start right here on this slide. At the top half of the slide, you will see our basic triac circuit. Let's discuss it a bit. On this side where it says input, this is going to go to your microcontroller. This is an optocoupler. This is to isolate the high voltage AC from the low voltage digital circuitry. The light emitting diode, when it's switched on by a microcontroller, will switch on what is called a photo triac. This will complete a connection through 180 ohm resistor from MT2 to the triac gate. Let's discuss a few things about our triac. First of all, you have to switch the gate on from pulses from MT2. It will not work from MT1, and you will lose your mind if you ever try to do that. It will never work. I don't care if you connected it directly to it, it won't work. You have to go through MT2. You do need this 180 ohm resistor for 120 volts, or you need a 360 ohm resistor for 240 volts. If the voltage value of your triac, if you're using it at 120 volts for instance, should be minimum of 200 volts. If you're going to use it on 240, I would use a 400 volt triac. Your load, here's your AC, you have your hot, you have your neutral. It doesn't matter where the load is. The load could be in the hot side, it could be in the neutral side, doesn't matter. You notice there's a 100 ohm resistor and a 0.1 microfarad capacitor. These two components across the triac form what is called a snubber. If I use a magnetic load such as a motor or a contactor, etc., these produce all kinds of switching noise which will cause false firing with the triac. So if you're going to use a magnetic load, use a snubber circuit. What are we dealing with here? In this slide, we have at the top your typical AC sine wave. Starts at 0 degrees, goes through 90, 180, 270, 360. You notice that at 0 and 180, the waveform crosses 0. We have 0 volts here, 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 and so forth. Anytime it crosses 0, that is the point from positive to negative or whatever. We need to know where those points are. We need a device called a zero crossing detector. That will tell the Arduino where I'm at in the AC sine wave. In other words, every time it crosses 0, we're going to produce a 5 volt TTL level pulse to one of the interrupts on the Arduino. Most of the interrupt pins are at digital pin 2 or 3. You can use either one. And we will see how to program it to do that a little later in the video. What is important is once the Arduino knows where where 0 is, or it's crossing, it can calculate a delay to determine where to fire the AC sine wave. And we're going to do this in half cycles. So the frequency coming out of the zero crossing detector is actually 120 Hertz for a 60 Hertz power line. If it's a 50 Hertz power line, it's going to be 100 Hertz. That is, I have to know at each half cycle where it crosses zero, and when I delay it, let's look at here. If I was to switch the triac on at exactly zero, it would stay off. There's not enough voltage there to cut it on. But if I was to trip the triac on here at this point, I read the zero crossing pulse, I calculate a delay, then trip it on there, I will get nearly the entire sine wave will cut on. Let's say at 20 degrees or something, I trip it on, I get the full sine wave pretty well. What if I sat here and delayed it for 179 degrees and tried to trip it over here? Too bad, I already missed most of the power that I could have had, and very little power will be transferred. Let's move on. Here's a zero crossing circuit that I built and designed a few years ago. I use it in my class to show how to control AC power with microcontrollers. Alright, here's your AC coming in. I used a step-down transformer. This says a 24 volt center tap. I would use a 12 volt center tap. That should work fine if you have one of those too. Center tap goes to ground. D1 and D2 in this grounded configuration form a full wave rectification. That is, if you knew about your power supplies and full wave, you will get 120 Hertz pulsating DC signal at this point here. Now, going through this diode D2, that of course is going to go to filter capacitor C2, and it's going to become straight DC, which is going to be regulated by this 5 volt regulator. That's going to operate the digital circuits in the Arduino. But down here, that diode, you'll still have the pulsating DC because the filtered DC is blocked by D2. The 120 Hertz pulsating DC through a current limiting resistor will go to the input LED, light emitting diode, in a transistor optocoupler. Anytime the optocoupler is cut on, it will switch on this photo transistor, and it will basically be switched to ground. There will be 0 volts at this point anytime the LED is turned on. The only time that it won't be turned on is when the sine wave crosses 0. Let's move down here to this connection. When it crosses 0, all of a sudden the LED is off, and I'll get a 5 volt pulse, a little short pip, at every half cycle. And that is fed into digital pin 2. Over here I have a 10K pot. This is connected to analog pin 0. What this is used for is the Arduino will calculate a delay based on the setting of this pot before it switches on the triac to control the power to a load. Here is the output circuitry, that fires the triac. On digital pin 4 is the power on switch. At digital pin 2 is just an 12, is simply a power indicator LED. I push switch, LED comes on. That tells me the power, the high voltage AC, has been enabled. Digital pin 5, connected through a dropping resistor, goes to the photo LED and the MOC 3011 optocoupler. Like the first slide in the introduction, we have a photo triac that is switched on. Here is our current limiting resistor. It's a 220 ohm. This device is called a diac. It is optional. You can just leave it out. I put it in there sometimes because it makes a more stable waveform when you're switching. But it'll work pretty well without it. Here is our triac. If you look at your AC, neutral goes to one side of the light bulb, but the hot side has to go through the triac to give it a full path to the light bulb. Thus, I can switch the triac on and off like a switch if I want it to, and just cut the light bulb on and off, or I can track the sine wave through the zero crossing pulses and cut it on anywhere I want to and control the power delivered to the light bulb. That is, it'll act like a lamp dimmer. As we will see, it'll be a little more fun than a lamp dimmer. Here's just a basic bit of software. I defined pin 5 as the triac pulse pin. I need an integer value val, which will be, you'll find out why in a moment. Okay, here in this case, I'm having to program digital pin 2 as an input, and I'm going to go ahead and pull the pin high through the internal pull-ups. The output pin is pin 5. It was defined. That's going to be my triac pulse. I'm going to use that to trip on the triac. And here I've attached the interrupt. The interrupt, of course, is where the zero crossing pulse comes in on digital pin 2, which was programmed as an input. In other words, now that the interrupt is attached and active, I don't even need anything down here in loop. It can just be empty. And I have not programmed an on-off switch into it. It just means that as I plug it in and cut it on and adjust the variable, the potentiometer, I can cut the brightness up and down on the light bulb. Now let's look. You notice again, look at attach interrupt. We're using interrupt 0 digital pin 2. We're going to go to a subroutine called ACOn, and it's going to be looking for the falling side of the zero crossing pulse. The pulse will go high, it'll stay there very short time, then it'll fall, and when it falls back to 0, that's when we trip on the interrupt, which jumps to this routine, ACOn. Here is the ACOn routine. We have a local integer temp. We're going to do an analog read of 0. That's where I tied in the 10K potentiometer a few slides back. An analog read 0, as I adjust the potentiometer, is going to give me a value from 0 to 1023. I'm going to multiply that by 6 and add 1000. Then I'm going to use temp in the delay microseconds routine. What happens, I jump to this routine when I got the falling side of the zero crossing pulse. This reads the pot, it calculates a delay in microseconds, and decides where I'm going to trip on the triac. Okay, I delayed. Now I'm going to trip on the triac. I'm going to output. The output pin is going to go high. Now let's note something in here. You cannot use delay in an interrupt routine. Won't work. You've got to use microseconds. You need to know that. So I've put the output pin to the triac high. It trips on the optocoupler, trips on the triac, and the light bulb should light up depending on the setting of the potentiometer. I'm going to delay 200 microseconds, and then I'm going to cut the output pulse off. So I produced a pulse width of 200 microseconds. To switch it on, and then I'm going to move that pulse along the from 0 to 180. Like I said, it's going to be 200 microseconds wide, and I'm going to move that pulse with this potentiometer circuit from 0 to 180, and I'm going to decide where I'm going to cut on the triac. Let's note up here, for instance, the reason I did this, I don't want to go, this is pretty well limited, 1024 times 6 is the maximum I could put out here, but if it come out analog read 0 times 6, what that would do is give me 0. The reason I used 1000 is I wanted to trip on the is I didn't want to go below a certain amount because that creates some headaches. So that's why I use these values. If it does nothing, if the pot is all the way down, it will trip on, it's not enough at 1000 to trip on anything. But it's just at the edge that the minute I begin to increase the potentiometer, it should start to trip it on. And you'll see an effect if you had an oscilloscope, something like this. The longer I delay the triac pulse, the less power is going to be output. Let's try a little bit of more sophisticated software. This time we're going to make a little nicer routine. I'm going to define triac pulse at digital pin 5. The on-off switch you saw in the earlier slide, I'm just going to call switch, SW. And the power indicator LED, I'm just going to call it ACOn LED. That's going to be at digital pin 12. Again, I set up digital pin 2 as an input. There's its pull-up. The triac pulse out pin is going to be an output again. Okay, where I connected the switch pin, that's going to be SW4, is going to be an input. A digital write SW high will cut on the internal pull-ups on the input pin, so when the switch is open it will read 5 volts if you put a voltmeter on it. I also set up the ACOn LED, that's the one connected to digital pin 12, and I made sure it's off. There's something missing here that that was in the original simpler setup. Let's go back a couple slides. In this setup, you notice I didn't attach the interrupt routine. There's a reason for that. Okay, here is my loop routine. This time the loop is not empty. First of all, I want to cut on the power only if I press the switch. I want ACOn to operate only when I press the switch. So I use this if not digital read switch. Alright, what this means, if I just read the digital read switch, it's always going to come back high and will make the statement true even if I don't press the switch, because the pull-up resistor on the open switch will make it read 5 volts. So I knotted it with the exclamation point, so the statement will be true only when I push the switch. Now I attach the interrupt and enable the power, the ACOn routine, and I also cut on the high voltage indicator LED. Otherwise, if I don't press it, it'll do a digital read switch, and now that the switch is open, it will be high and will meet the condition, and it will make sure the interrupt is detached, that is, the power is off, and it will make sure the ACOn LED is also off. That's it. Press switch, you got power, you can adjust it. Don't press switch, it's guaranteed to be off and do nothing. And so that's the run through on the electronics and some of the software. Next we will be viewing the an actual video of the live working circuitry. Let's go there next. Alright, what's pictured here is another Arduino project. I'm going to move over and focus in a little bit on the components. Of course, you see a light bulb off to the upper left of the picture. Before we get to that, I'm going to zoom in on what the electronics are, give you a little better look. Of course, here's an Arduino microcontroller. That small chip there is an optocoupler. This is a, of course, variable resistor or pot connected to one of the Arduino's analog inputs. This is a triac assembly or AC switch. This transformer here is used to isolate the oscilloscope in the background that we will be looking at shortly from the 120 volts AC. What the object here is, well, I'm going to zoom it back and we'll operate it and you'll see just what it does. If I adjust the control, the light bulb gets brighter and dimmer compared with the, as you can see. Okay, somebody's going to sit here and say, well, okay, you've made a fancy lamp dimmer. It's a little better than that. Not only can the Arduino control the power to the lamp, and by the way, that could also be a transformer, it could be a heating element, it could be any number of items. Its ability as a microcontroller means it can use various sensors to control temperature. What's actually going on with the AC is it's using it actually has two optocouplers on that board. One operates as a zero crossing detector that produces a pulse at 0 and 180 degrees on a sine wave. The Arduino detects that pulse and then is programmed to switch on the AC waveform, and it's doing it in half cycles. So it's doing this for each half cycle waveform. Let's put it like this. On a 60 Hertz line, the pulse width is 16.7 milliseconds. That's 0.0167. But now it's even operating on half of that, something like 0.0088384, something like that. And in that time period, it can decide at what point to cut the AC, and if you have the time span from 0 to 8.3 milliseconds, where you switch that half cycle on determines how much power is going to be delivered to the load. Just like this. Let's take a look at it on the oscilloscope to get a better idea what we're dealing with. Alright, what you're going to see here, if you look at the bottom of the screen down here, if you look at, you can barely see a little pip or a pulse. And this is your AC sine wave. As I move the pulse around, I will be able to cut off more and more of the AC sine wave and deliver less power to the load. That is, the lamp gets dimmer. The top is the output power to the AC, and you see the zero crossing pulse, and where it's delayed, that's the triac firing pulse, and above is of course the AC waveform. And that's how we control AC power with a zero crossing pulse, a programmable delay circuit, and a triac. This would be useful if you have some of the new solid state temperature sensors, for instance. I've used something like this with a cooler to hatch chicken eggs. The idea is, okay, the Arduino can measure the temperature in the cooler. It's cool in there, you want full power, but as the power comes up, but as the temperature rises and gets to where you want it set, it will gradually reduce the power, and it can be programmed to the point that it delivers just enough power. In this case, I was warming it up with a light bulb. And it can be programmed to feed just enough energy into the system to make up for that's lost in the environment. This is called proportional temperature control. It's very handy, it's very accurate, and they would have to use it in industrial processes. Not too far from me is a company that makes ammunition and explosives for the military. They have to use very, very precise temperature controls in their manufacturing processes, and this is how they do it. Incidentally, this system I experimented with it once and it worked pretty well. That if you use 3 Arduinos, 3 zero crossing pulses and a single control, I actually used this thing to control the speed on a 3-phase motor. And it actually worked quite well. So there's a lot of possibilities for this, particularly in the areas of temperature control, and it may be motor speed control too. You may use a TAC to send a feedback pulse to the Arduino, and it can control the motor speed. It would have to be an AC motor. It could very easily control motor speeds. Like I said, if you're going to use it on motors, you are going to have to use a snubber. And that completes this video.